Imagine this. You and your twin both celebrate your 30th birthday today. You step onto a spaceship and travel close to the speed of light. For you, the journey feels like just 5 years. But when you return to Earth, your twin is now 80 years old, while you've only aged to 35. How is that even possible? How can time run differently for two people born on the same day? Does the universe actually allow us to travel into the future? And if time can bend, what about space itself? This isn't a thought experiment, it's a scientific reality, proven by countless experiments and confirmed every single day by the technology you carry in your pocket. Welcome to Einstein's theory of relativity, here on Astronomical Library. For centuries the universe seemed simple. Sir Isaac Newton taught us that space was like a giant stage, and time was the steady clock ticking in the background. No matter where you were in the cosmos, a second was always a second, a meter was always a meter. It felt obvious, almost undeniable. Think of it this way. If two people dropped an apple from a tree, one in London and one in New York, they would both expect the apple to fall in the same way, governed by the same invisible force we call gravity. To Newton, the rules of the universe were absolute. Space was fixed. Time was fixed. But as the 19th century came to an end, cracks began to appear in this perfect picture. Scientists discovered a problem with light. You see, light wasn't behaving like sound or water waves. No matter how fast you moved, light's speed never changed. Imagine standing in the rain. If you run forward, the raindrops should hit you differently than if you stand still. But with light, that isn't the case. Whether you're racing toward it or speeding away, it always hits you at exactly the same speed. 299.792. 458 meters per second. This was confirmed by the famous Michelson-Morley experiment in 1887. They built one of the most precise scientific instruments of their time, trying to measure even the tiniest difference in the speed of light. And the result? Nothing. Zero difference. Something about our understanding of space and time was terribly wrong. And then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything we thought we knew about the universe. Einstein's special theory of relativity, published in 1905, rests on two simple but revolutionary postulates. First, the laws of physics are the same for all observers, no matter how fast they are moving, as long as they are not accelerating. Second, the speed of light in a vacuum is always constant, about 300 million meters per second, regardless of the motion of the source or the observer. These statements may look innocent, but from them flows an entirely new picture of reality. Let's unfold this step by step. Imagine time as one dimension woven together with the three dimensions of space. Together, they form what Einstein called spacetime. Every object moves through spacetime at the ultimate speed limit, the speed of light. When you're sitting still, you're moving through time at full speed. 1 second passes for you, or 1 second passes for everyone else. But if you start moving through space, say, climbing into a spaceship and approaching the speed of light, something astonishing happens. To keep the total speed through spacetime constant, you borrow from time. Your motion through time slows down. This is why the twin paradox works. One twin travels fast through space, so they must move more slowly through time. When they return, less time has passed for them than for the twin who stayed on Earth. Let's make this more vivid. Picture yourself holding a flashlight inside a moving train. To you, the beam shoots straight up and down, bouncing between the floor and the ceiling. But to someone standing outside watching the train, the beam isn't just moving up and down, it's tracing a diagonal path. That diagonal is longer than the straight line. And since light always travels at the same speed, the outside observer concludes that time inside the train must run slower to make the math work out. This isn't just imagination. In 1971, the Haffel-Keating experiment flew precise atomic clocks on commercial airplanes around the globe. When compared with identical clocks on the ground, the airborne clocks ticked more slowly, exactly as relativity predicted. And today, relativity runs your life without you noticing. GPS satellites orbit Earth at thousands of kilometers per hour. Without relativistic corrections, your phone's GPS would be off by up to 10 kilometers every single day. The fact that your Uber arrives within meters is thanks to Einstein. But if time can stretch, what happens to space? It bends the other way. From Einstein's equations, objects moving near light speed actually appear shorter in the direction of motion. This is called length contraction. Let's imagine a spaceship that, when at rest, measures exactly 100 meters long. To the astronauts on board, nothing changes. They walk from one end to the other and still measure 100 meters. But to an observer watching from Earth as the ship flies past at 90% the speed of light, it no longer looks 100 meters. It appears only 44 meters long. Why? Because, just like with time, space adjusts itself to keep the speed of light constant for all observers. Now here's a fun thought experiment. Suppose you have a garage that is only 50 meters long, and you want to fit a 100-meter spaceship inside. At normal speeds, impossible. But if that ship is flying close enough to light speed, an Earth observer would see the spaceship contract and just for a moment, it would fit perfectly inside. Of course, from the astronaut's perspective, it's the garage that seems contracted, not the ship. Relativity makes reality itself depend on your point of view. While we can't directly see length contraction in daily life, high-energy particle accelerators confirm it constantly. Subatomic particles traveling near the speed of light live longer than expected, and travel farther than their normal lifetime would allow, because in their frame, space is contracted. All of these strange effects are tied together by Einstein's most famous equation, E equals mc. This equation says that mass itself is a form of energy. A small amount of mass can be transformed into an enormous amount of energy, because you multiply that mass by the speed of light, squared an unimaginably large number. Let's put numbers on it. 1 gram of matter, just a paperclip, contains about 90 trillion joules of energy. That's enough to power an average American household for thousands of years. To compare, the Hiroshima bomb released about 63 terajoules of energy. 1 gram of mass, if fully converted, contains more than 1,000 times that energy. Every single second, the sun converts 600 million tons of hydrogen into helium, releasing the energy that lights and warms our planet. This is why nuclear reactors work. They turn a tiny fraction of matter into energy. This is why the sun shines. It is literally burning mass into light. And this is why nuclear weapons are so devastating. They unlock even a small fraction of the energy bound in matter. So far, Einstein has shown us that time is not absolute. Space is not absolute. Even mass is not absolute. It is deeply connected with energy. All of this emerges from just two postulates. The consequences ripple through every corner of physics, from the ticking of your GPS satellites to the burning core of the sun. But this was only half the revolution. Special relativity left one major question unanswered. What about gravity? How does the force that keeps planets in orbit and galaxies bound together fit into this new picture of space-time? Einstein would spend the next 10 years searching for the answer, and when he found it, he didn't just modify Newton's law of gravity. He completely replaced it with a breathtaking new vision of the universe. If special relativity shattered our idea of time and space, general relativity would rewrite the very nature of gravity itself. The principle behind general relativity. Einstein realized that gravity is not really a force, in the Newtonian sense. Instead, it is the curvature of spacetime itself. Statement of the theory. Matter and energy tell spacetime how to curve. Curved spacetime tells matter and light how to move. This elegant principle replaces Newton's invisible force with a geometric picture. Mass bends the stage on which the universe plays out. Einstein first imagined himself in an elevator. If the elevator is in deep space, far from any stars, and suddenly accelerates upward, you would feel pressed to the floor. Drop an apple, and it would fall to the floor just as if gravity existed. But if the elevator were sitting on Earth, you would feel exactly the same. Einstein concluded. Acceleration and gravity are indistinguishable. This equivalence principle became the foundation of general relativity. To picture it, imagine spacetime as a vast rubber sheet. Place a heavy ball in the middle, it creates a dent. Smaller balls rolled across the sheet spiral toward the heavy one, not because they're being pulled by an invisible string, but because the sheet itself is curved. In reality, Earth bends space-time around it. The Moon orbits Earth, not because an invisible hand pulls it, but because it is following the straightest possible path in curved space-time. The same is true for planets around the Sun. But the most stunning prediction was that even light, which has no mass, would follow the curvature. In 1919, during a solar eclipse, Arthur Eddington photographed stars near the Sun. Their positions appeared shifted, because the Sun's mass bent their light. Newspapers around the world announced, "Einstein's theory triumphs." Overnight he became a global icon. Today, this bending of light, called gravitational lensing, is a powerful telescope for astronomers. Entire galaxies act as cosmic magnifying glasses, bending and distorting the light of even more distant galaxies behind them. Some of the most breathtaking Hubble images are examples of Einstein's theory written across the sky. General relativity also predicts that time itself runs slower in stronger gravity. At the surface of Earth, time ticks just a little slower than it does far out in space. The effect is tiny, but measurable. In fact, GPS satellites orbit higher up in weaker gravity, so their clocks run faster than those on Earth. Engineers must apply both special relativity, because the satellites are moving fast, and general relativity, because they're farther from Earth's gravity. Without both corrections, GPS would fail within hours. This effect was beautifully shown in the movie Interstellar. On a planet near a black hole, 1 hour on the surface equaled 7 years for the crew waiting far away. While dramatized, it is rooted in real physics. Perhaps the most extreme prediction of general relativity is the black hole. Imagine compressing the Sun into a sphere just 3 kilometers wide. At that density, space-time curves so steeply that nothing, not even light, can escape. The boundary is called the event horizon, a one-way door into darkness. For decades, black holes seemed like mathematical curiosities. But now, they are observed everywhere, in the centers of galaxies, devouring stars, even colliding and shaking the fabric of space-time. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow in galaxy M87. The dark circle against glowing plasma is direct proof of Einstein's vision. General relativity also predicted something breathtaking. Massive objects in motion, like 2 black holes colliding, should create ripples in spacetime itself, gravitational waves. In 2015, the LIGO Observatory detected these waves for the first time. 2 black holes 1.3 billion light-years away had spiraled together, releasing more energy in a fraction of a second than all the stars in the observable universe combined. Those tiny ripples reached Earth, stretching and squeezing space itself by less than the width of a proton, but our instruments were precise enough to measure it. So, let's step back. With special relativity, Einstein taught us that space and time are not fixed, they are flexible, relative to motion. With general relativity, he revealed that space-time itself is dynamic, able to bend, stretch, ripple, and even collapse. What Newton described as a force, Einstein described as geometry. And that geometry rules the cosmos. From the orbit of planets to the dance of galaxies, from the ticking of your GPS to the collision of black holes. The deeper we look, the more we realize. Einstein didn't just change physics. He changed our very perception of reality itself. So, what have we discovered together? Einstein didn't just give us another set of equations. He rewrote the very fabric of reality. Special relativity shattered the illusion of absolute space and time. It showed us that motion changes how we measure both distance and time itself, and even mass transforms into pure energy. General relativity took us further. It revealed that gravity is not a force pulling objects, but the very bending of space-time caused by mass and energy. From black holes to gravitational waves, it gave us a new lens through which to view the universe. Relativity in everyday life. And yet, this grand theory, ICT, just for black holes or distant galaxies, touches your life every single day. Every time you use Google Maps or check your GPS, you rely on relativity. Without Einstein's corrections, your phone would be lost within kilometers after just a few minutes. The very nuclear energy that powers stars and the destructive force of atomic bombs comes directly from the equation E=mc. Even the expansion of our universe, the discovery that galaxies are rushing away from us, depends on Einstein's curved spacetime. Einstein's ideas are not just abstract, they are the foundation of modern civilization and our deepest cosmic knowledge. But perhaps the most profound gift of relativity is not just in physics, it's in perspective. It reminds us that reality itself depends on where we stand, how we move, and the scales at which we observe. Time is not the same for everyone. Space is not the same for everyone. What we call absolute may only be an illusion. If our very sense of time and space can bend, stretch, and ripple, what else about the universe might we be blind to? Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible. But have we truly comprehended it yet?" Because relativity, as revolutionary as it is, may just be one chapter. Beyond it lies quantum mechanics, dark matter, dark energy, the mysteries that even Einstein himself could not solve. And that is where our journey continues. This is Astronomical Library, where the universe is not just studied, but felt. If today's journey bent your mind just a little, imagine what's next. Subscribe, share your thoughts in the comments, and join us as we explore the frontiers of space, time, and reality itself.